Swerve drives. What are they and how do they work? A swerve drive is an omnidirectional drivetrain that essentially be split up into two parts: wheel rotation and pod rotation. You can rotate the wheels just like any standard drivetrain, but let's take a closer look at the gear configuration. This setup allows the wheel to freely rotate around its axis and rotate as well, so the wheel can rotate in different directions. For example, you can rotate the wheel like this, with the central axis, the coaxial axis, still transmitting power to the wheel. This makes for an omnidirectional drivetrain. In this particular swerve, I've chosen for a 7.2:1 ratio with 64mm outer diameter wheels. I've calculated this using the iLight drivetrain calculator, which turned out to be optimal for this specific module. These wheels use the AnyMark Grey Grippy thread, which is perfect for swerve drives due to their high friction coefficient and ease of use. But different swerve drives also use screws to secure the thread to the wheel. I've chosen to make the wheel very thin. This wheel is 15.6mm, which increases toe sync, thus increases traction for the robot. This does come with a slightly higher current draw for your pod rotation servo, this one, but that is insignificant. During the design of this module, I aimed for a 1:1 top ratio, low center of mass, and an overall small size for the modules. The 1:1 ratio on top makes for minimal coaxial effect and has minimal friction due to the GT2 2mm belts I use. I use bigger pulleys because the bigger pulleys, they provide less friction, thus making your wheel spin faster. I am also making use of Rev's 5mm hex shafts because it's a high speed, low torque application, and I'm making use of aluminum 8-rack standoffs because 8-rack steel is overkill for fast moving applications and it can easily hold the weight of the robot in dead axles. The wheel is supported by a dead axle, as I just mentioned, and the wheels are hot swappable. What this means is that if you take out these screws, you can take out the wheel and the bevel with it. This is so you can easily swap your wheels anytime you need to. For the pod rotation, I'm using a 2.5:1 ratio using gears right here. And then using pulleys, I'm using a 1:2.5 ratio. So the overall ratio of this is 1:1. This is essential because for swerve drives, you need to know where your pod is facing. So for example, if it's facing diagonally this way, the absolute analog encoder inside of your servo will know which direction it's facing. So you don't have to do any software-based zeroing of your pods every time you run your robot, every time you reset your robot. As for the motors and servos, I'm using the Mini Plus servos from Axon, as you don't need as much torque as the Max Plus servo does. And I'm using the Gobilda Bear motors. These motors are really nice because they are small, they're cheap, and they have 1/8 inch pinion, which is compatible with most 3D printer pulleys, which are easier to source. I'm making use of low profile encoder caps. These low profile encoder caps, they shave off quite a few millimeters from the bottom, making sure this module has enough ground clearance. They also have side cable outputs, which makes it so you don't have to put your cable through the rectangle here and have like the additional 5mm of cable below your robot. Instead of that, you can just run the cable through the side, your power cable, because you don't need an encoder cable, and still have all that area left. Package your motor as close to the ground as possible, as you can see right here, which is essential if you want a low center of mass. Because I'm using smaller gears right here, I'm also able to use smaller bearings. So this bearing right here is a 2-inch inner diameter and a 2.5-inch outer diameter, which is really nice because most FTC swerves, they tend to use a 2.5-inch inner diameter and the 3-inch outer diameter. So this saves quite a few millimeters to the sides. Here's a banana for scale, if you wanna take a look at how big the module is, or let's say how small the module is. If you put these modules side to side, you can package your entire robot in 266 millimeters, which is very nice, as you can make smaller robots which are way more maneuverable. They're smaller, they're lighter, so they have better acceleration and are overall just faster. Alright, so let's talk about the costs of this specific Swerve drive. So 4 of these modules, they will cost you about $800 US, which the majority of the cost is the servos and your gears. The rest of the pod is 3D printed, it's CNC milled, as for this polycarbonate for example. Alright, there you have it, the mechanics and design choices of my coaxial Swerve drive. The Swerve drive module used in this video are available for download in the description. Keep in mind that the CAD is supposed to be a source of inspiration instead of using these pods in your actual robot, as these pods are not tested. If you've got any more questions regarding Swerve drives, feel free to leave a comment or to reach out to me on